Francesco.
Hi,
So
Nelly.
Francesco is going to be talking about integrating AI and XR technologies in professional MBSE curricula. And the floor is yours,
Thank you very much.
Francesco.
Good afternoon, everyone. My name is Francesco Ciriello, and I'm a lecturer in engineering education here at King's College London. In the session, what I wanted to do is to share a bit of a reflection on our experience developing and delivering a new CPD course in collaboration with the University of Oxford. And in fact, the special mention goes to Ajit Jalkar and Lars Kunze, who actually led the course from the Oxford side. The course was titled Digital Twins, Enhancing Model-Based Design with Augmented, Virtual, and Mixed Reality. And we ran it for the first time last November. And we wanted to use it as an opportunity to roadmap future educational directions in model-based engineering design. And we're really interested in defining the role of emerging technologies for digital twins. For DevOps, for AI-based modeling and operations. But more importantly, our main focus was to try and examine the role of game engine virtualization in how engineers develop model-based design practice. The course involved collaborations from several industrial players, including the MathWorks, Unity, Siemens, Jaguar Land Rover, and also the Digital Twin Consortium. So we got a lot of great input from industry in the course. Today, I'll tell you a bit about the framework we created to deliver the course and highlight a number of challenges that we face in delivering educational content around this topic, which I think you'll find very interesting. And I'll try and leave some time at the end so we can keep the open discussion going about the field and get some input from you, because we really do welcome feedback. So this is how we started the practical sessions of the course, with this schematic that we borrowed from the MathWorks, which somewhat highlight the role of digital twins in moving from their traditional role in operations and sustainment of reusing models for operational decision-making to try and push the traditional MBD engineer to think about digital twins as simulations that grow as an asset through product life cycles, rather than being confined to this operational world. And the idea closely aligns to the sort of agile processes that we're so familiar with for continuous improvement, which are commonplace in software engineering. And what we were really keen was to try and stress that operating digital twins in the field was the key mechanism to close the feedback loop between product cycles. So nothing too new about the philosophy here, but this is the framework we use to propose value for digital twins. We then move on to, once we had established a common grounding on the traditional view of model-driven engineering, we sought to map out opportunity areas for different emerging technologies. And we started by examining the role of artificial intelligence at different stages of MBD, so starting from the left-hand side, looking at, say, unsupervised methods to mine data from previous life cycles of digital twins, and perhaps improve requirements and system architectures from this feedback. We then moved towards the middle, and we started looking at how AI can support data-driven modeling for SysID, for surrogate models and sort of ROMs. We try to get some of our learners to pick up some basic skills that would support some of these workflows. And finally, we discussed how to use AI in operations in the deployment of AI-based listeners, for example, in anomaly detection applications, or as agents for optimizing decision-making systems. We also investigated how to incorporate augmented, virtual, and mixed reality technologies into the same workflow by considering how what we would call all of these technologies XR, how XR technologies can enhance the way we, say, visualize products that we plan to model and build through computer-aided design, how we might create virtual worlds using photorealistic engines to support control system design and testing, which can also be then deployed to mixed reality hardware, such as flight or driving simulators, for further, say, operator-in-the-loop testing. And finally, how XR technologies can enhance different operational processes like manufacturing, like inspection, and like teleoperation of, say, unmanned vehicles or robots. So we created a case study to try and convey the roles of all these technologies in the course, and we tried to create practical components inside it too, that looked at multiple aspects of sort of an enhanced MBD workflow. So we examined how a team of engineers might design and operate a fleet of package delivery drones, and it offered a good framework to develop simulation-driven algorithms for both design and operations. Looking at motors, looking at battery health, looking at how to simulate faults in the copters, and even how to run reduced order models, say, for the aerodynamics of flight. So we organized the case study by first exploring traditional themes in model-driven engineering. So on the top line, you can see how we started looking at design of experiments, reusing models for operational decision-making, and also some techniques showing how to synchronize a digital twin model by, say, assessing the condition of an asset from streaming data. And these are really cornerstones of, say, digital twin practice that we wanted our learners to get some practice with. We then moved on to show how the boundaries between model and a physical asset fade in a sort of modern DevOps. We looked at how to use simulation to generate edge cases, for example, motor faults, and use data to improve or generate models through system identification or parameter estimation techniques. In the second day of the course, we started looking at emerging technologies, starting from AI and delving a bit deeper in data-driven modeling, and then looking at how AI can be used in decision-making systems. That's sort of the operational intelligence on the slide. But for the final part of the course, we focus on building interfaces and engineering use cases to XR software. So for the rest of the talk, I'll focus on these technologies as they are sort of less commonly explored in engineering practice. So the main tension that became readily apparent as we started delivering the course was that we typically model systems with a whole spectrum of fidelity. And on one end, we were developing simulations in sort of engineering IDEs like MATLAB and Simulink to show some of the workflows. But on the other end, we also wanted to deploy some of those simulations into platforms such as Unity and Unreal to take advantage of a wealth of features that come with photorealistic simulators. And this is an interesting schematic that resulted in our attempts to first explain the game engine technology to sort of engineers, and then map it to model-based engineering workflows. So let's say if a game developer designs a new virtual world, they'll first build their players and their environment as objects in a gaming engine. And on top of that, they would define dynamic elements such as interactions or articulations to start modeling the interactions between them. And these would then filter through a series of animations or kinematic or dynamic models or event triggers to start creating richer interactions between the virtual world and, say, the actors or players, which would be rendered through some kind of engine. Now, we're seeing more and more engineers practice similar workflows. And this is how we try to map some of these elements into engineering world, from the creation of assets in CAD, where we might build actors, which might be CAD models of, say, pumps, of cars, of drones, and so on. These actors will be built in assemblies, typically in some proprietary language that exists in a CAD package that defines the joints and their relative position. And then we'd have to import these into a gaming engine with tools like Unreal Datasmith or Unity Pixies. And then these scenarios and physics would be primarily driven by simulations. So we had to think about how to build interfaces between realistic physical simulations and some of these XR technologies that have much faster physics, but less of a lower fidelity. So this was definitely the main challenge that we had for the course, and we tried to summarize, say, what a basic definition for an interface between a simulation and a simulator. We also tried to define different types of workflows that are common and that engineers use, which we named the playback, co-simulation, and standalone deployment. And I'll go through these quickly before I wrap up. So a typical workflow that an engineer might use, say if they're designing a drone, is to first of all record the output of a simulation that, say, they developed in a design tool, and then play it back into a gaming engine. For example, they might want to display the path a drone has taken into a virtual world, and by processing it through a virtual world, they can collect sensor data like images or LiDAR data, and which they can then reanalyze in sort of a design tool. The second workflow involves building a live interface between a simulation and a simulator, and these need to be synchronized by some form of pacer, and we need to build some form of messaging bridge that occurs through some form of middleware. Common ones used in engineering are things like MQTT for simple messages, and more common in some industries, we're seeing ROS being a big player for, or at least the UAV robotic space. And finally, the last sort of interface that we mentioned was to look at how we can package some of our simulations and deployment into an XR or a gaming engine tool, and many simulation tools now offer, well, for some reason they call compilers, which I never understood, or some form of SDK for packaging that allows for deployment of simulations into gaming engines. So we looked at how you might call, say, different types of simulation engines from these tools. So that's what we covered. We started this brand new course, and we were quite ambitious. We were really trying to map these emerging technologies in engineering practice and covering a whole breadth of technologies. And I can see sort of Stefan's question, which was a lot of content, and we covered it in 2 days. So we just tried to give a flavor of all these technologies. The whole course was 6 days, but some of the content we looked at here was covered in 2 days. And one of the major challenges that I'm sure will come to no surprise was how to build interfaces between simulations and simulators, not even getting to the whole idea of synchronization between the two, which becomes even more challenging to build those live interfaces. So we welcome feedback on the course structure and some of these reflections. The course will run again, and it was the first time we ran it, so some of this was sort of new to us as well. And yeah, I hope you enjoyed the presentation.